So what is inside this black box? It is what we shall call algorithms. And an algorithm, if familiar, is what? It's kind of a fancy looking word, but it's a simple thing. What is an algorithm, if anyone knows? Yeah, just step-by-step instructions for solving a problem. That's it. That is an algorithm. Step-by-step instructions for solving some problem. So what might be a problem that we want to solve? Well, I'm reminded of, and I'm reminded of 5th grade. My homeroom teacher was trying to teach us as effectively as she could how to follow directions correctly. And at the time, it was a complete disaster. But I always remembered from that example the demonstration that she did, because it lent itself, although she didn't use this word at the time, to this notion of computational thinking, or thinking like a computer, if you will, whereby you want to solve something correctly. But to do so, you need to be fed very precise instructions. And this is easier said than done. And so, in fact, to recreate this, thanks to the team here, we have a plate. We have a loaf of bread. We have a jar of creamy Skippy peanut butter. And we have a jar of Smucker's Concord Grape jam. And then for the invariable need, a whole lot of paper towel and this one knife. And so let me propose that for just a moment, I'll play the role of a computer, or maybe in this form, like a robot who's implementing some algorithm, where you guys are the programmer, the person who's supposed to feed me instructions so that I can solve a problem. And the problem here will be to implement, perhaps no surprise, a peanut butter and jelly sandwich. Easy to sort of do intuitively if you grew up eating these things. But if you've never really thought about how to teach someone else to do it, and that someone else is not as sort of forgiving as another human, where we humans have conventions of just reading between the lines, computers can't do that. They will only do what you tell them to do. And as such, they are less powerful in some sense than we humans. So what's the first step for making, with these ingredients, these inputs, if you will, a peanut butter and jelly sandwich? Open the bag of bread, I heard. Correct, but not really what you had in mind, perhaps. But that's OK. The bag is open. So what might a more precise step 2 be? Say again? Remove 2 slices. OK. Put those 2 slices on the plate. Drop the knife? OK. Unscrew the jam. OK. Grab the knife. Put the knife in the, what? Oh, thank you. Right. Grab the knife from the other end. Someone from farther back, perhaps? Stick the knife in the jam. What's that? Take it out. OK. Again. Put the knife in the jam. Ow. Scoop it. OK, we're halfway there. Now what? Spread the jam with the knife across the bread. Oh, evenly. Let's be careful here. OK. Right. OK. OK. Next. OK, so I think we did this first. We did this, then we did that, then, OK, I'll take some liberties. OK, and now we put it in again. Scoop a little bit out, I heard this time. Onto the other slice of bread, thank you. Spread it evenly. Next time, have me use my right hand, please. OK. OK. And? Thank you. Put the jam side on the peanut butter, and delicious. OK. OK. Thank you very much. So a silly example, to be fair. But just realize how much opportunity there was, even in something as simple as that, for ambiguity or scenarios you didn't anticipate. And indeed, among the things we're going to do today as we begin to formalize these ideas with code, with programming code, are how you think about breaking down problems into their constituent parts, considering what should I do if this happens? What should I do if this happens? What should I do if this happens? Because unless you anticipate the kind of silliness that I was deliberately acting out there, who knows what the computer might end up doing. After all, odds are everyone in this room, like me, has seen like a spinning beach ball or an hourglass on your computer, or your Mac or PC freezes or crashes, and almost always that's just the result of some human error. Someone at Google or Microsoft or Facebook or wherever made some mistake. He or she did not anticipate some situation, didn't anticipate you typing in a word that you didn't anticipate you running 20 programs at once, didn't anticipate some scenario, and so as such, the computer's behavior was effectively undefined, and so the incorrect solution was outputted. So how do we begin to think about this? Well, it would be ideal if we somehow formalize this by way of actual code. And we'll do that with sort of another old school problem, one that's a lot more digital these days, but it's still with us today. Whether you have an Android phone or iPhone or anything else, odds are you have like a little app for your contacts or your address book, and in there are a whole bunch of names, probably alphabetical by first name or last name, and a whole bunch of telephone numbers and maybe more information like emails and so forth today. But the physical incarnation of that icon on your phone is this old thing, a phone book. And if I wanted to look for an old friend like, say, Mike Smith, how might I go about finding him in this old school phone book? Well, just as in my digital form, I might just scroll through the list looking for him. So could I look at the first page, look down, not see him, turn the page, look down, not see him, turn the page, look down, not see him, and so forth. Is this algorithm correct? Yeah, it's correct. It's kind of dumb, right? Because it's going to take forever to get to Mike if there's like 1,000 pages here, but it is correct. And it's the equivalent, really, of sort of slowly, methodically scrolling through your list of contacts without the luxury of like searching or autocomplete or the like. Well, I could do a little better. Back in grade school, I generally learned to count by 2, so I could instead do 2, 4, 6, 8, 10, 12. I'm flying through the phone book now, clearly faster. But is that algorithm correct? No, why? Yeah, I might miss some, right? Like Mike, just by chance, might be sandwiched between, so to no pun intended, between the 2 pages that I'm flying past, and I might miss him. But I can at least fix this mistake or bug, so to speak. A bug is a mistake in a program, just human error. If I hit like the T section, T comes after Smith, so I could maybe double back at least 1 page and solve that bug. So it costs me a little bit more time to double back, but if I do it right, it only costs me like 1 extra page turn. So better, and now correct. But obviously, no one in this room is going to look for Mike Smith by starting on the first page. Where are you going to roughly look? You know, in the middle, maybe a little toward the end, because you know where S's are. And so you open the book to the middle, you look down, and you see the M section. So I haven't gone far enough. But what's nice about this old school technology is that we can now tear this problem in half, throw half of it away, and be left with fundamentally the same problem, but a smaller version thereof. This now is maybe not 1,000, but 500 pages, but it is the same problem. And I can apply the same logic, go roughly to the middle, look down. I went a little too far this time, the T section, but I can again tear off almost a quarter of that problem, leaving me now with a total size of maybe 250 pages after dividing in half twice now. And now I can repeat and repeat and repeat. And so long as Mike is in the phone book, I should ultimately find him once and only once on the final page of the phone book, at which point I can call him. So the real question then is, how much better was this? It's a little wasteful. You can't sort of undo here in the analog world. But let's consider how we can think about how good that algorithm was, the one that we all probably took for granted and should have started with. Well, if here's a simple plot, and on the x or horizontal axis is the size of the problem, so number of pages in the phone book, or however you want to measure it. And then the y or vertical axis is time to solve, so maybe number of seconds, number of page turns, however you want to count up the steps. That's a relationship, size to time. And the first algorithm, I'm going to draw like this, a straight line in red. And I'm going to call it n, where n is just like the number of pages in the phone book. Computer scientists tend to use n as a variable, so to speak, just a symbol. And it's a straight line for the following reason. If the phone book gets a little longer next year, a little longer next year by like 1 page, that means I might have to spend 1 more step looking for Mike. So the slope of this line is linear. There's a 1-to-1 relationship between number of pages Verizon or the phone book company puts in the book and the number of page turns I need to make. The second algorithm, though, is also a straight line, but it's lower, drawn here in yellow. And n over 2 means it's twice as fast, or equivalently takes half as much time, because for a given size problem, if you kind of follow my hand straight up, the yellow line should be below the red line, because I'm flying through the phone book 2 pages at a time, so it should take me half as much time. But if I use the first algorithm, I have to go all the way up to the red, which measures that number of seconds. But the third algorithm is a fundamentally different shape. And this is where the sort of beauty of computer science and algorithms specifically comes out. It doesn't become straight ultimately. It looks like it's gradually easing off, but it's going to do this forever. It's just becoming such a slow increase in time, you can't even really see it, especially if the screen were even wider. And we'll call this logarithmic, log n, more on that down the road. But the shape is fundamentally different. It's curved. And what's powerful about this, and you can think about it much more easily intuitively, if Verizon next year doubles the size of the phone book, because like maybe Cambridge and another town merge together into one book, no big deal. Because if Verizon doubles the size of the phone book next year, how many more page turns do I need to find Mike? Just one, right? Because I just split the problem in half one more time, no big deal, instead of flipping through an additional 1,000 or 500 pages. And so this intuition with which you entered Sanders today, odds are you can harness it already to solve problems more effectively, so long as you start to notice the patterns and the sort of useful inputs with which you can solve problems. But we need to begin to formalize the process. We need to be able to express ourselves a little less organically than we did with the peanut butter and jelly. So how might we more methodically express that algorithm, the phone book, all of which, for which we probably nonetheless have an intuitive understanding? Well, let me start counting at 0, just because programmers and computer scientists tend to start counting at 0, because that's like all the light bulbs are off, so you might as well start there. And then step 0 would be pick up phone book. It's sort of an action. Do this. Step 1 is open to the middle of the phone book. That's pretty much what I did a moment ago. Step 2 is look at the names, another action or verb. Step 3, if Smith is among names. So this is a different construct. And that keyword here is going to be if. It's a question you're asking yourself. It's kind of a proverbial fork in the road. If Mike is among the names on the page you're looking, then call Mike. And I've deliberately indented it because in many computer languages, indentation means logically that you should only do step 4 if line 3 were true, or the answer to that question is yes. Else, if Smith is earlier in the book, he's meant to be to my left, then step 6, open to the middle of the left half of the book. So that's when I tore it in half, threw it away, and then repeated on the left half. Else, if Smith, then go back to step 2, a key step. Now that I've divided the problem in half, and I'm looking in the middle of the left half, the problem is fundamentally the same as I claimed before. Just do the same thing, but on a smaller problem. And what's beautiful about this algorithm, it's recursive, so to speak, as we'll see down the road too, is that you keep doing the same thing, but because the problem keeps getting smaller, eventually you're not going to do this forever. You're going to find the answer you're looking for. And so we go back to step 2. Step 8, if Smith is later in the book, to my right, open to the middle of the right half of the book, and then again, go back to step 2. Else, what's the fourth scenario to consider? Yeah, what if Mike isn't in the phone book? He's unlisted. We'd better anticipate that lest my program crash or my computer freeze because it doesn't know what to do if Mike isn't there, so I'll quit in this particular case. And now let's tease this apart by highlighting in yellow those operative verbs or actions. Henceforth, we're going to call things like these yellow words functions, so to speak, in a programming language. These are verbs or actions, and I've called them out, albeit in English, because there's no one language here. This isn't like a formal vocabulary we're introducing. It's just my most succinct way of expressing that algorithm, and that's what pseudocode is. It's English-like syntax that anyone in the room should hopefully be able to follow if you're nice and clean and precise about it. But there's another type of keyword in here, and that's the if and the else if and the else if and the else. These are the keywords that languages typically use to represent these forks in the road. Go left, go right, go here, go there, do different things. And each of those decisions, if you will, is based on the answer to a question. And these questions we're going to call Boolean expressions, named after a person named Boole years ago. And a Boolean expression is just a question with a yes-no answer, or really more technically, a true-false answer. And notice, the fact that everything falls into buckets of 2, yes, no, true, false, means we can use those light bulbs really to our advantage. Maybe off shall be no or false. Maybe on will be true or yes. Just using a one light bulb can we represent any of these answers to these questions. And so those are Boolean expressions. And then lastly, there's these things. Go to step 2, which is perhaps the most explicit. It's inducing some kind of loop or cycle. do something again and again. And all of these ideas, functions, conditions, Boolean expressions, loops, and more, are going to permeate the several languages that we explore over the course of the semester. But of course, this unto itself is not yet real code. And today, in just a little bit, we're going to dive into real programming code, albeit graphically, using a language called Scratch, and then follow that on later next week with a programming language called C.